Have you ever been in a building that just feels right? You know, it's cool in the summer, warm in the winter, and the AC isn't constantly blasting? Well, that's not an accident. It's the genius of solar architecture. And today, we are diving deep into it.
And really, this question is at the heart of everything. We build these sealed boxes and then spend a fortune on electricity to fight against the weather outside. It's kind of crazy when you think about it. So what if we just stopped fighting? What if we designed buildings that actually work with the sun and the wind?
So here's our game plan for today. We're going to start with the big idea, then get into the nitty-gritty of tracking the sun. After that, we'll see how designs change for different climates, check out some really clever tools, and finally, look at how we actually score a building's performance. Okay, let's kick things off with the core concept. And I want to be clear, this isn't about just sticking some solar panels on a roof and calling it a day. No, this philosophy goes way, way deeper. It's about designing a building from the very first sketch to be in sync with nature. So what is solar architecture? Well, at its heart, it's all about something called passive design. And what that means is making really smart, simple choices about the building itself, its shape, what it's made of, even which way it's facing, so that it can heat, cool, and light itself, naturally. This dramatically cuts down on how much work the machines have to do. Now, to make any of this work, architects have to be total experts on the sun. Seriously. The #1 secret to all smart solar design is knowing exactly where the sun is going to be in the sky at any hour of the day, any day of the year. And they do this using 2 key angles. You've got the altitude, that's just how high the sun is off the horizon, and then you have the azimuth, which is its position from east to west, kind of like reading a compass. If you can master these 2, you can predict exactly where sunshine and shadows are going to fall on your building. It's like a superpower. And this is the absolute game changer. This simple diagram reveals the fundamental trick of all passive design. In the summer, the sun takes this really high path across the sky. But in the winter, it stays super low, making a much shorter trip. This one predictable difference is everything. It means we can design a building that easily blocks that high summer sun to stay cool, but at the same time welcomes in all that low winter sun for free heat. Brilliant, right? Okay, but knowing where the sun isn't a one-size-fits-all solution. A design that's perfect for a hot desert would be a complete disaster up in the cold mountains. So how do architects take these universal principles and apply them to specific local climates? Well, let's take a look at the playbook. If you're in a hot, dry place like Rajasthan, your enemy is intense heat. So the strategy is to use thick, heavy walls that soak up heat during the day and let it out at night. You also use courtyards to trap cool air. But if you're in a warm, humid spot like Kerala, the humidity is your biggest problem. So you do the total opposite. You want lightweight buildings with massive openings to get as much air moving as possible. See, it's all about using the right strategy for the right challenge. And this is one of my favorite examples of that solar geometry in action. It's so simple but so clever. For a south-facing wall that gets hit by that high summer sun, a simple horizontal overhang, think of it like the brim of a baseball cap, works perfectly to shade it. But on your east and west walls, the sun is really low in the sky in the morning and evening. A horizontal shade would do nothing. The sun would just sneak right underneath. So for those walls, you need vertical fins to block that low-angle glare. All right, beyond just placing windows and shades correctly, architects have a whole bag of incredibly clever, low-tech tricks up their sleeves. These are design elements that are literally built into the building that act like natural heating and cooling systems. Check out the Trombe wall. It's perfect for colder climates. Basically, it's a big, dark, heavy wall with a sheet of glass in front of it. The sunlight goes through the glass, gets trapped, and heats up the wall. Because the wall is so massive, it holds on to that heat all day long. Then, when the sun goes down and things get chilly, that wall slowly radiates all that stored warmth back into your house all night. It's literally a solar-powered battery for heat. And for hot climates, you've got the wind tower. This is an ancient idea, but it's incredibly effective. The concept couldn't be simpler. The tower reaches up high, above the roof, to catch breezes that are cooler and stronger up there. Then it just funnels that fresh air down into the living spaces below. It's a natural air conditioner with 0 moving parts and 0 electricity. How cool is that? So we have all these amazing ideas and clever designs. But how do we actually know if they're working? How can we measure performance and compare one material to another? Well, that's where the energy scorecard comes in. First up is something called the U-Value.
It basically measures how quickly heat can move through material, whether it's a wall, a roof, or window. And here's the only thing you really need to remember. A lower U value is always better. A low number means it's a great insulator, and that's what you want for the outside of your building.
The second big one, and this is mostly for windows, is the SHGC, or Solar Heat Gain Coefficient. It's just a number between 0 and 1 that tells you how much direct heat from the sun a window lets in. Now with this one, good totally depends on where you live. If you're in a hot climate, you want a low SHGC to block out that unwanted heat. But if you're in a cold climate, you want a high SHGC to let all that free solar warmth pour in. All right, we've covered the principles, the tools, the metrics. I think you're ready. It is time for a little pop quiz to test your solar IQ. First question. So you've got a west-facing window and it's getting blasted by that low afternoon sun. What's your most effective shading device? Is it A, a horizontal overhang, or B, vertical fins?
And the answer is B, vertical fins. If you picked that, you got it. Remember, that low-angle sun would zip right underneath a horizontal overhang. You need those vertical blades to block it effectively.
Okay, question number 2. That clever device, the Trombe wall, what is its primary job? Is it A, natural ventilation, B, daylighting, or C, passive heating? The answer is, of course, C, passive heating. It's that amazing solar battery we talked about, soaking up the sun all day to keep you cozy all night. And that really brings us to the most important point of all. We tend to think that a smart building has to be packed with sensors and complex technology, but maybe the most innovative building is the one that's designed so perfectly, so in harmony with nature, that it barely needs any tech at all.